All right, so we're in section 9.2 now. We're talking about series and convergence. So we're going to talk about what it means for, what a series is, what it means for a series to converge, and then today's nice because we get to talk about two kinds of series where we can actually find the sum, rather than just show that it does actually have a sum. So sequences, a lot of times it can seem like sequences are you know, we talk about sequences and then we jump into series and then sequences don't matter anymore. But sequences are, they play a central role in series. So let's first talk about what we mean by a series. So we're going to use an infinite sequence to represent infinite summation. So if a sub n is an infinite sequence, then the sum, I'm going to sum from n equals 1 to infinity of the terms of the sequence. This is our infinite series. I'm just going to say dot, dot, dot. So we're going to summing to infinity. So this is an infinite series. And to find the sum, what we're interested in is do infinite series have a sum? Can we add them up and come up with some finite number? So to find the sum of this infinite series, we look at the sequence of partial sums. So this is why sequences are still play a central part in series, is because the sum of a series has to do with the sequence of partial sums. So our first partial sum is just a sub 1. Our second partial sum is a sub 1 plus a sub 2, and so on. Dot, dot, dot. And our nth partial sum is just the sum of n terms. The way we define the sum of an infinite series, the way we decide if our infinite series has a sum, if our infinite series converges, is if the sequence of partial sums converge. Then our series converges. So we're going to look at this sequence of partial sums. That's how we decide if a series converges. So if the sequence partial sums converge, and that's what we just talked about in the first section, is how do we know when sequences converge. The sequence of partial sums converge, then the series converges. So that's why sequences are important, because that's how we define the sum of our series. So let's be just a little more formal with what we've said here. Everybody good with this? So more formally, So we're going to say for the infinite series, and we're summing from n equals 1 to infinity of a sub n. The nth partial sum, we'll talk about nth partial sums a lot. The nth partial sum, S sub n, is just the sum of n terms, like we said before. So if the sequence S sub n converges to some sum S the limit S is called the sum of the infinite series. And the opposite also tells us if our series diverges. If S sub n diverges our sequence of partial sums, then the series diverges.
You can prove both.
So yes, if our sequence of partial sums diverge, then the series diverges. Now there are some tests that we'll use that will show one but not the other. But in this particular case, if the sequence of partial sums converges, our series converges. If the sequence of partial sums diverges, then the series diverges. Because the sequence of partial sums is how we define the sum of the series. So if the sum diverges, then the series diverges. Soon we need a fire drill, right? All right. So let's look at a couple of examples and look at partial sums and figure some things out about partial sums. So as an example, we want to look at the sum n equals 1 to infinity of 1 over 2 to the n minus 1. So I'm just going to write out a few terms here. 1 plus 1/2 plus 1/4 plus 1/8 plus, does this look familiar?
Wait, I'm sorry. So a sequence is like one always plus infinity or separate.
The sequence, so the sequence, if we were talking about the sequence 1 over 2 to the n minus 1, the sequence would just be the list of numbers 1, 1/2, 1/4, 1/8. The series is them added together, the terms added together. Yes. So that's the difference, and it's important to keep that difference separate, is that the sequence is just the list of numbers, the series is the terms added together. So let's look at the partial sums. So these are the terms from the joke I told earlier. So our partial sums. So S sub 1 is 1. S sub 2 is 1 plus 1/2, or 3/2. S sub 3 is 1 plus 1/2 plus 1/4. So our third partial sum is 7/4. Do one more, 7. Is it 7/8?
Yeah.
Yeah, I think we reduced to 7/4, right? So we have 8/8 plus 4/8 plus 1/8. Okay. And then S sub 4, 1 plus 1/2 plus 1/4 plus 1/8, and we get 15/8. And if we keep going, if we figure out our pattern, in order to use this definition to find the sum, what we have to do, S sub n, is all of these 1 plus 1/2 plus 1/4 plus ... We have to figure out some kind of pattern for this partial sum. And that can take some work. And finally, our at the end, we'd have 1 over 2 to the n minus 1. And we're looking for a pattern, some kind of generating pattern for these fractions. If you're very clever, or otherwise it might take a lot of work, you would see that this is 2 to the n minus 1 over 2 to the n minus 1. If we're looking for a pattern that generates these partial sums. And that's the same as 2 minus 1 over 2 to the n minus 1. So you're looking for this pattern. And as n approaches infinity, as we keep adding more and more of these, as n approaches infinity, this term becomes less and less and less, and it approaches 0. So our sum limit as n approaches infinity is of 2 to the 1 minus 2 to the n minus 1 is just 2. So the sequence of partial sums is going to converge to 2, so the series converges to 2.
You know, I understand this, but I pressed the first part of the
Oh. Right. So these are the terms are how many drinks each of the infinite mathematicians order. Right.
Wait, 2 walk into a bar, I can't remember.
What infinite number of mathematicians walk into a bar?
Yeah, I feel it was like
It's a big bar. But they only had to serve 2 beers. So using this is how we would use the definition of the sum of an infinite series to find the sum of an infinite series. We usually want, because figuring out this pattern can be difficult, we look for shortcuts. We look for an easier way to do this. So let me look at one other example where there is an easier way, and then we'll talk about a couple of specific types of series. All right, let's look at another example. We want the sum. All right, let's focus, guys. The sum n equals 1 to infinity of 1 over n minus 1. Now, to find the sum of this type of series, we could start listing terms and try to figure out a pattern. But let's see if we can be a little smarter.
Isn't it undefined when n equals 1?
I want this. Sorry, this should be n plus 1. Thank you, Cole. Yeah, if I put minus, then I'd have a problem. All right, so we could list out terms. We could try to figure out a pattern for our nth partial sum and see if we can find the limit. But let's be a little smarter about this. When we see a fraction like this, what does it ring any bells for anyone? What if we were asked to integrate dx over n times n plus 1? What would we have to do to integrate that?
Yeah, partial fraction.
Partial fractions. We have this fraction where we have these terms mixed together. So when we see a sum like this, when we see a fraction like this, you should think partial fractions. And you can use if you use the cover-up method to do partial fractions, just let me know that that's what you're using. When I was in school, I was never taught the cover-up method, so I always just used the algebra method. So 1 over n times n plus 1 equals a over n plus b over n plus 1. And when we solve this, when we figure out these partial fractions, it turns out that a is 1 and b is negative 1. So we end up with 1 over n minus 1 over n plus 1. To go through that decomposition, this is what we get. So what we're looking at is the sum, n equals 1 to infinity, of 1 over n minus 1 over n plus 1. Now let's write out some terms of our sequence. So for n equals 1, I get 1 minus 1/2. Plus, for my second term, I get 1/2 minus 1/3. For my third term, I get 1/3 minus 1/4 plus ... What do we see here? Everything cancels out. This 1/2, negative 1/2 cancels with this 1/2. This negative 1/3 cancels out with this 1/3. We're going to have the same thing, the same pattern repeating for every set of terms. So these cancel, these cancel, these cancel, and we can keep going. And our limit as n approaches infinity the limit is 1. So our series converges to 1. This type of series has a special name. We call this type of series a telescoping series. So it's one of the types of series that we can find the sum. The reason it's called a telescoping series, it's like the pirate spy glasses, that it just kind of collapses down. So let's write a little bit more about telescoping series. So this form, when we end up with this type of form, the form b sub 1 minus b sub 2 plus b sub 2 minus b sub 3 plus b sub 3 minus b sub 4, etc., is a telescoping series. When we see one of those, when we see a fraction that we can use partial fraction decomposition for the terms of our series, that's our hint that we're going to have a telescoping series. And all the terms cancel except b sub n and b sub n plus 1. So we end up with all of our terms cancel, So if b sub n approaches a finite number, our series will converge. So if we can express a series in this form using, and it comes up when we have to use we have a fraction when we can use partial fraction. When we can express a series in this form, it's very helpful for finding the sum. So this is one of the few kinds of series, telescoping series, one of the few kinds of series where we can actually find a sum. Most of the time what we can show is the series converges or the series diverges. We can't, it's very, very difficult to find the sum. So a telescoping series is one type where we can find the sum. Our first example, where we have the sum from n equals 1 to infinity of 1 over to the n minus 1, is another type of series that we can find the sum. This is a geometric series. That's another type of series where we can find the sum. A geometric series can be written in the form our sum from n equals, and usually with geometric series we start our index at 0, n equals 0, a r to the n. And if we write out some terms, that's a plus ar plus ar squared plus plus ar to the n. And we're saying that a doesn't equal 0. If a equals 0, we just have 0. And we call r the ratio, or the common ratio. So each term has this ratio of r, some power of r in it. And we can show that, and we'll do the little demonstration in just a second. If the absolute value of r is greater than or equal to 1, then our geometric series diverges. And if our absolute value of our ratio is less than 1, and we need, I'm going to make it a little more, move my if over here, 0, less than or equal absolute value of r, less than or equal to 1, then the series converges. And our sum converges to the sum a over 1 minus r. So telescoping series and geometric series, two types of series where we can actually find the sum, which makes them nice. Now, did you guys, last year, did you go through the proof of this? Proof of the sum. It's a nice, short little proof, and it's nice. It's a good one to be familiar with. So let's prove that this is the sum of an infinite geometric series. So I'm not going to do a lot of proofs, but we'll do a few. So our sum, S sub n, our nth partial sum is a plus ar plus ar squared plus ar to the n minus 1. And I'm saying n minus 1 because we're starting our indexing at 0, at n equals 0. Now I'm going to multiply by r. Multiply both sides by r. So r s sub n equals ar plus ar squared plus ar to the third plus, and this should be a dot 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 here, plus ar to the n. And now I'm going to subtract and I get s sub n minus r s sub n equals a minus ar to the n. So I'm subtracting these two. So s sub n, factor out an s sub n here, times 1 minus r equals a times 1 minus r to the n. Factor out an a. And then I'm just going to divide. So s sub n equals a over 1 minus r times 1 minus r to the n. And if our absolute value of our r is between 0 and 1, the limit as n approaches infinity of r to the n is 0. And we just end up with a times 1 minus a over 1 minus r. So there's our proof that this is the sum of an infinite geometric series. So nice, short, not difficult proof. This one and the showing what the sum of a arithmetic series are kind of nice little proofs. Do we need to see an example of finding the sum of a geometric series? I think you guys should be pretty good with that. So we have two types of series that we can find the sum of now that we know the sum of a geometric. We know the sum of a geometric series. If we know that our ratio is between 0 and 1. The absolute value of our ratio is between 0 and 1. We can find the sum of the geometric series. If the ratio is larger than 1, then our geometric series diverges. If we can express our series as a telescoping series, we can use partial fractions and write it as a telescoping series. We can find the sum of a telescoping series as long as our terms approach a finite number. Questions? So the homework in this first part is just working with geometric series, working with telescoping series, and then Friday, tomorrow, we'll talk about a couple of applications of geometric series. So our homework, 12. All right. Now, what was the